Hi. This is the second video in the series on exponential models. The first video was introducing the exponential models and also worked through a series of examples trying to demonstrate some of the different types of questions you can ask about an exponential model. In this discussion here, I'm going to talk about half-life models, and a little bit about doubling time models. These are reformulations of the exponential model, which make it easier for us to work with them outside of the world of mathematics. The third video in the series will be concerned with the Newton cooling process and also some financial models. Please recall that the general exponential model has an equation that looks like this. The amount at time t, a of t, is the initial amount, a of 0, and we multiply by e to the kt. That's our general exponential model. When we're going to use this for working on problems outside of mathematics, this parameter k becomes somewhat opaque, and what we would like to do is to find ways to make our models more meaningful to those that want to work with those models. One of the ways of doing that is through what are called half-life models. These are actually just special formulations of the exponential model. A good example is radioactive decay. When you have a radioactive substance, there will be a parameter associated with it, always denoted by the Greek letter lambda, which is the number of years it takes for half of the atoms in that sample to undergo radioactive decay. As they do that, they disappear as the original substance and reappear as the decay products. And so every lambda years, half of your sample will disappear. Now, to make use of the half-life in our model, what we do is we note that every time we have a period of lambda years go by, we have to multiply by 1/2. The way to build that into a formula is to think of time as divided into half-life units. So you divide time by lambda, and that divides time into t over lambda units of length lambda, which is the half-life. For each of those half-life periods, you multiply by 1/2, so you get a of t is a of 0, 1/2 to the t over lambda. And this is our formula for a half-life process. Let me just do an example so that we can see what's going on. Iron 55 has a half-life of 2.7 years. And in this question, we're asked how much of a 100-gram sample will remain after 6 years? And how long will it take for a 100-gram sample of radioactive iron 55 to decay to 20 grams? Note, iron has other isotopes with radically different half-lives. So we should always say iron 55 here. Okay, so the formula is that a of t is a of 0, 1/2 to the exponent t over half-life. We'll measure time in years, so we'll have to make sure that every time measurement in here is reconciled to be measured in years. So from the formula, a of 6, the amount after 6 years, is 100 times 1/2 to the 6 over 2.7. So I just put t equals 6 in this formula, use my calculator, and I get 21.43 grams. That's how much is left after 6 years. Part B asks, how long will it take for the 100 grams to decay into 20 grams? So now we're asking for the quantity t, And we know that when we reach t, we will have 20 grams left. So 20 is 100, 1/2 to the power t over 2.7, and what we want is t. So if we just divide 20 by 100, we get 0.2 is 0.5 to the t over 2.7. The variable is in the exponent. We can't really solve for it up there. We have to use logarithms to bring it down onto the line. So we take logarithms. We get log 0.2 is t over 2.7 log 0.5. Solve for t and we get 6.27 years. So it's really just like the other version of the exponential models, where we in fact could end up solving for t or at or a0 or a ratio. And as we're doing that, we are going to have to take logarithms sometimes to solve the problems.